When designers pitch a new application, they usually showcase the default state. The dashboard is populated with colorful charts, profiles are complete, and every metric is glowing green. It's the perfect scenario, the happy path, and it's what developers naturally aim for when they sit down to write code. But in the real world, the environment is rarely that cooperative. Wi-Fi connections drop out on moving trains, database queries return zero results, and users make input mistakes at the worst possible times. If a software team only builds for that perfect scenario, the application fractures the moment friction occurs. A slow internet connection results in a jarring blank white screen, or a simple typo generates a cryptic wall of code that tells the user nothing useful. Avoiding these failures requires an invisible network of design conditions, known as screen states. These are specific, designed responses to loading times, missing data, permissions, and system errors that catch the user the moment the ideal path breaks. Reliable software is defined by how it protects and guides the user when things go wrong, rather than how it looks when everything operates smoothly. Think about what happens the first time a user opens a brand new app. Data takes time to fetch over a network, and a proper loading state sets an immediate expectation during that wait. By showing a skeleton layout and disabling buttons to prevent duplicate clicks, the UI signals that the system is actively working. When that loading phase clears away, a brand new user often has no data to display. Instead of presenting a barren panel, the empty state must explicitly tell the user what is missing, such as a lack of assigned tasks, so they aren't left wondering if the screen simply failed to load. A functional empty state also provides a solution, offering a clear button that guides the user to their next logical action, like creating their first record. Without these specific steps, software feels broken to the end user. To them, a blank screen with no context is indistinguishable from an application crash. Well-designed empty and loading states transform a confusing lack of data into a reassuring, guided onboarding experience. Now let's imagine that user is attempting to populate their new dashboard by filling out a complex data entry form. To keep bad data out of the system, developers use a disabled state. This keeps critical actions, like a final submit button, locked and unclickable until every required field is properly satisfied. If a user attempts to bypass these guardrails with invalid input, like typing an email address without an @ symbol, the system triggers a validation state. This documentation highlights the strict rules for effective validation. The error message must appear directly adjacent to the field, explain specifically how to fix the issue, and avoid using language that blames the user for the mistake. Proper validation turns potential dead ends and frustration into minor, easily correctable course adjustments that keep the user moving forward. Sometimes the friction is a security wall. If a user inadvertently navigates to a restricted area, they hit a permission-denied state. This screen has two requirements. It must clearly offer a resolution, such as a link to contact an administrator, while strictly preventing any restricted data from being exposed in the view. When catastrophic failures occur, like an API crash or a failed save, the system triggers an error state. As this source text stresses, the interface should explain what happened to the user while strictly avoiding the exposure of sensitive technical details. Helpful error states avoid dumping raw server logs onto the screen. Instead, they note that a connection issue occurred and provide a clear mechanism to retry the action. Handling system failures gracefully preserves user trust. It proves the application remains stable and in control, even when its external connections break. Modern software often pulls information from multiple sources at once. If primary metrics load but a secondary feed times out, the UI relies on a partial data state to show what is available while explaining the specific isolated failure. Complexity increases with the integration of artificial intelligence. Generating a summary takes significantly longer than a standard database query, requiring a processing state that sets proper expectations for the user during the wait. AI output is also notoriously unpredictable. This documentation requires the interface to indicate low confidence when appropriate, warning the user that generated suggestions need human verification before they are applied. As applications integrate these unpredictable elements, designing granular, expectation-setting states becomes the only way to maintain a coherent user experience. After navigating the loading screens and correcting the validation errors, the user finally completes their task, triggering the success state. For critical tasks, a well-implemented success state confirms the action and proactively suggests the next logical step, guiding the user directly to a review screen or the following required workflow. Viewed holistically, these individual states form an architectural safety net. Collectively, they reduce support questions, improve accessibility, and prevent the application from failing silently in the background. Mapping out every edge case and error screen is what separates a flimsy utility from a polished, enterprise-grade product. Great design is the invisible, structural empathy that guides a user through the chaos of the real world by catching them when the happy path fails.